Okay, any question about the previous session? Today we want to continue our discussion about normalizing flow models, starting from this idea that if we have a simple or base distribution over Z, then we can, by transforming the random variable using a transformation, we can get into a more complex distribution. For example, this one is a bit more complex than the original one because it is a rotated shape, okay, and also scaled. So if I can be able to calculate the density here as a function of the parameters of this transformation, then I can tune these parameters such that the resulting distribution is as much near as possible to my data distribution. How? By maximum likelihood estimation. Okay, this was the general idea. The point was that here we show that especially in this example, this example is very simple, but it can show to some extent the general case. You know, here we assume that the distribution here is uniform. Okay, and argued that the distribution here also must be uniform, but it's some change. Because if we do not have any change, for example, here is 1/4 and here is also 1/4, you will see that here we do not have area equal to 1, which is one of the axiom of every PDF. This was the problem. So this 1/4 is not correct for this space. We call it X space, okay? And we show that by dividing the distribution here to the Jacobian, to the ABS, to the absolute value of the determinant of the Jacobian of the transformation that we call it F, we reach to the correct PDF here. So the PDF here can be reached by dividing the PDF here in the original or base space by the absolute value of the determinant of the Jacobian. This was the simplest case, but in much more complex case, assume that I have an arbitrary distribution here. For example, it is designed over this circular area, okay? And it is non-uniform here. Non-uniform. It is to some extent more generalized than this one. Because here we have uniform, assume here is not even uniform. It is arbitrary. I want to justify how this term works in the general case, okay? Because here it was a very simple one. In the resulting, after you transform it, with an arbitrary invertible transformation F, which is parameterized by theta, okay? You will reach another shape here. Assume that this is the shape in the X space, okay? But if you focus on one differential area here, a very small, it is a differential area, okay? Here is x1, here is x1 plus dx, I mean the differential length. And also in this space, x2, and this is x2 plus a differential. We know that for this point, everything about the middle point can be applied to the whole area, to the whole box, small box. Do you agree? Because it is differential length. Nothing changed in the differential length to some very large, okay? So I can assume that the PDF here is a fixed, and also the F function here can be linearized, similar to this function. can be switched to an affine transformation. How? By Taylor expansion of this function. It is not important to understand the detail, just we want to have an overview how it can be applied into more complex case, okay? The transformation can be approximated using, for example, a Taylor expansion in this point. So we have exactly the same as here. We have a box where PDF is uniform in this box, similar to here, but here the box is complete box. And also the transformation is also a simple affine transformation. So we can apply everything here, and we reach a point here, another area here, and we know that the PDF here can be approximated using the PDF or in the original space Z of the corresponding point. I mean, we call it G of X. Here, assume that this is my X vector, okay? Divided by the Jacobian of F. The Jacobian is not different between the transformation and its affine transformation, okay? So it can be applied, the idea can be applied into the general case. So what we need is just to divide the PDF in the base space with the determinant of the Jacobian of the transformation in that point. Or equivalently, because the transformation is invertible, we have G, which is the inverse transformation, and you can, instead of dividing by the determinant of the Jacobian of F, you can multiply it by the determinant of the Jacobian of G. This is a property of invertible functions or transformation. So with this approach, I can easily calculate the distribution over the X in the X space. And we see how I think we oh no, we do not have, I think, these presentations. I think the last point was here, maybe. Okay, let's start from the start of the session. Okay, in normalizing flu, we assume Z is coming from a base distribution, and the base distribution is easy to sample. This property brings you with interesting feature for generation of new samples. If Z is easily generated, easy to sample. We define a flexible parameterized transformation f theta from the base distribution Pz to estimate the data distribution P theta x. And now we want to optimize the transformation such that the distribution in the X space is as near as possible to your data distribution. Everything is, the approach is this one. And we know that minimizing the KL divergence is equivalent to maximizing the expected of your model over the data coming from the true data distribution. These are equivalent optimization problems. Okay. But let's compare it with VAE. In contrast to VAE, here we can easily calculate the exact data likelihood. Why? Because the transformation is invertible. You know that if you have X, if you observe X in your let's say observed space, then you know what is your latent corresponding to this X using a function called G, and we know that G is the inverse of this F transformation. So this is the main difference between VAE and normalizing flu, but this property provides you with the exact calculation of the likelihood. We know that for the VAE, we can at most calculate what about the likelihood? We can at most calculate the elbow in the point X, which is a function of model parameters and also the parameters of approximate posterior. Okay, your best estimation to the likelihood is using elbow in variational autoencoder, a lower bound to the point likelihood. But here you can exactly calculate p theta of X. So, for example, in the case of anomaly detection, maybe they are much more efficient than VAEs. But VAE, on the other hand, due to the invertibility of the normalizing flow, you need the latent space and the visual and the observed space to be of the same dimension. It means that if you are, for example, using normalizing flow to model images, your latent space is also the same dimension as your images, which may not be tolerable in some cases. For example, the images are of the dimension of 1 million, and the latent space is also the dimension of 1 million. So there is no abstraction in the latent space. You know, the dimension of both observed and latent space are similar. So there is no abstraction. There are some abstraction to be applied further. Why? Because when you, if you have X, and if you design the transformation so you have access to G, using G you can go to the Z space. And we know that Z space is a simple distribution. Then you can work on applying some coding here so that you can gain some compression, okay? But in nature, what you are doing is not compressing the input, the observed data. But if you have something coming from a Gaussian distribution, you have much more efficient coding scheme for that data. It is important to know that you can apply further processing here. But what you are doing in flow models is here, and here you do not have any compression. Okay? The next one is that finding a meaningful or attribute direction is not possible in flow models because of that dimension preservation. Why? Because abstract level are needed when you have some bottleneck in your model. The model needs to learn some high-level representation so that it can represent the data in the lower dimensional space. You know, for example, you have face images of dimension 1 million, but here in the Z space of a VAE, you have just 100, for example, dimension. The model is forced to learn something which is suitable to represent the data in that low dimensional space so that it can reconstruct data from the low dimensional space. But here you do not have any bottleneck. If you have 1 million, you have 1 million again in the middle, in the latent space, and you can adjust the distribution is changed. The distribution is changed to a very simple distribution. Okay? These are the main difference between these two approaches. Okay. Now the main important part is because we want the likelihood here. Because we want the likelihood, the Jacobian and the determinants is very important to be calculated efficiently. So we want to focus on how to derive the distribution in the observed data. Okay, let's assume that your transformation is x is equal to f theta of z, and each element, the first element of the x is the result of one function u1 of the input z, the second is u2, and until the end, they are exactly the same dimension, both x and z. Then the Jacobian matrix is a is this matrix, and we know that the first row is the Jacobian of the first, is the gradient of the first input with the first output with respect to the input. I think I have made a mistake here. Yeah. Unfortunately, I made a mistake here. These are all z. The partial derivative of u1 with respect to z1, not x1. These are all they are not correct. Okay. This is z1, zd, z1, zd. Okay. So this is the definition of the Jacobian, but you pay attention that this matrix is of dimension, for example, for an image is of dimension 1 million times 1 million. So it is very large, and you should care about the determinant, the calculations, okay? And we know that if I access to this Jacobian, irrespective of the complexity and the resources needed to for calculation, I can easily calculate the distribution in the observed data in a closed form, in this closed form, you know. For the data X, first I should find the corresponding Z, this is the corresponding Z, and calculate the base distribution in that Z, and then multiply it by the determinant of the inverse of the absolute value of the determinant of this Jacobian matrix. Everything goes. So first I have X, I find the corresponding Z here, and I also use it here. I can write down G of X here too, but I write it Z. This is Z. You should calculate the Jacobian in that point, and calculate this determinant, then the absolute value, then inverse it, and multiply the value of the PDF in the base space by that number. And this is responsible to change the area we see in the in our example at the start of the course. Where the box was changed, the area was changed. This updates the area so that the resulting distribution is a valid distribution in the observed space. Okay? Everything is clear? And also on the other hand, here also I made again the mistake. Pay attention that these are x1, xd, x1, xd. I make them in the vice versa manner, okay? Assume that I have the inverse transformation G, which is the inverse of free or forward transformation. Then you can represent it using this form, and Z1 is equal to the output of a function V1 applied on the input X until the end. And the Jacobian of this inverse transformation is equal to this form, and we know that these are all X. And then you have a point X. What should we do? First define the Z here. Calculate the PDF of base in that Z. This is not correct. The area is not correct. It should be updated. The update using the inverse transformation is this term. The absolute value of the determinant of the Jacobian of G and input X. Here is is a bit simpler. Why? Because you can input X to this Jacobian. This Jacobian, the input to this transformation G is X, so you can easily input your own X into this Jacobian. This is another form. They are equivalent. There is no difference, and you can use both of them, but there is efficiency considerations on how and where to use which of them. And you will see how to use the best one. Any question? How we can calculate the distribution in the observed space? Is it clear? Yes.
So kind of related to the simple uniform example.
Yes.
Is Z still from the simpler distribution?
Yeah, generally Z is selected from a simple distribution, not uniform. Generally it is a Gaussian again, of the same dimension, yeah, with your observed data. Okay. But you know, we are looking for flexible transformations. So you cannot expect one layer of transformation or one simple transformation can work for you. For example, you are thinking of a transformation which is invertible, and you say, okay, I apply this transformation and then find the distribution in the target space or in the observed space. Then I update the parameters and everything works. No, you should propose some flexible, because you want to transfer from a Gaussian, a simple Gaussian, into the data distribution, and we know that the data distribution is much more complex than a simple Gaussian distribution. Okay, so this transformation, although should be still invertible, but it must be flexible. It means that it should give you the ability to change the distribution easily in the target space. So the idea is to compose different transformation with each other. You think of some transformation you can compose different transformations with each other to reach a more complex and flexible transformation. This is exactly the similar idea to the deep learning models that try to compose different layers to reach a more and flexible and expressive transformation. But there, the transformation is not invertible. Here, we are subjected to be, we are forced to be invertible. Okay. What can we do? Assume that I have L different transformation, and I'm confident that all of them are invertible. There is no doubt that they are all invertible. Okay. We will talk about what is a good invertible transformation. Okay, we will introduce the invertible transformation next. So if I, you know that if any of these transformation is invertible, if I make a composite function transformation using all of them, the resulting transformation is also invertible because each part is invertible, and you can reverse the process in each of them. So you can reverse the process in the resulting composite transformation. So here we assume that each of these Fi are invertible transformations, and we know that F theta is also invertible. For the notation simplicity, I will not write down these theta with subscript anymore. So pay attention that Fl is also a parametric transformation. It is not a simple transformation with no parameters. Okay. So this is an idea to build complex and expressive transformations. This is the idea, and we know that if each of these F is invertible, I can easily design the inverse transformation of this F theta and call it G theta, and just the change is that the reverse order. In the forward transformation, I applied F1 first and Fl at the last. In the inverse, I should cancel the effect of Fl. So I apply GL, then Fl minus 1, GL minus 1 until the start. So can easily design the inverse transformation for the composite. Is it clear? Okay. But there is another important point, how we can calculate the determinant in this case. Because the most important part is how to calculate the density in the target space or in the observed space, and that needs the determinant of this transformation. And we want to talk about that issue. Okay, just a notation for the next few slides. Assume that I have a Z in the original base space and apply it to the composite transformation. Z is passed through the F1 transformation. I call the resulting vector Z1 with this notation, and also till the end. And if I define ZL equal to X, I mean the last one, and Z0 equal to Z to input, then I can have this compressed notation. And also, using the reverse transformation, I also have this notation for the reverse transformation. And we know that how they can be interpreted, because FL and GL are inverse. GL is the inverse transformation of FL. Okay, just a notation. So the Jacobian of this transformation can be easily calculated using the chain rule. Chain rule state that the Jacobian of this transformation is the Jacobian of the first line times the second times the third until the last one. I just write down the chain rule here. This is exactly the chain rule. Chain rule for vector function transformations. Okay, so the Jacobian of your function is the multiplication of the Jacobian of each transformation in the composite. And pay attention to the order. The order is important. Although they can be applied in any order because the dimension matched, they are all of the dimension d times d, but But pay attention, the first one is here, then the second, and the order is much more, is the most important point here. The order matters. So I design a composite transformation like this, okay? So instead of one layer of transformation, I have L layers of transformation, and I know that if I want to calculate the density in the target space, I can use this formulation. And again, I know that the Jacobian of the F can be calculated using matrix multiplication. So things becomes much more important in terms of efficiency. You should calculate the Jacobian of each of the transformation. Assume again the image 1 million times 1 million. Each of them are 1 million times 1 million. Then you should multiply them together and reach another 1 million times 1 million matrix, which is used here. And then you should calculate the determinant of that 1 million times 1 million, the absolute value, the inverse, and then times it times the p of p in the point of g theta of x. So everything should be designed very carefully because any inefficiency can lead to interactability. Is it clear? Why do we need? Yes.
There are ways to like approximate the determinant.
Instead of approximating, we design them efficiently. We design them such that these calculations can be easily done. But
when you say we design it for efficiency, like what's that mean? An example, because it's an element-wise matrix multiplication.
No, for example, if this transformation are such that the resulting Jacobian, for example, is higher upper triangular or lower triangular, then the determinant is the multiplication of the element on the diagonal. Yeah. Okay. We will design them. Do not think of this transformation. The transformation will be introduced next. We just want to build the original foundation, how to calculate the density. Assume that here we have lots of resources and you even can calculate the multiplication of big matrices, okay? We will then talk about the efficiency. So I can have a more expressive transformation. They are all nonlinear, so the composition is much more nonlinear than each of them. Again, think of the idea of deep learning. You composite nonlinear transformation with each other. Here also, the same procedure is being done. Okay, so I have the resulting distribution. So if I use composite transformation now, I can calculate the data likelihood again, and there is no problem by using the chain rule. Okay, so assume that I have Z. We know that we generally have X, but just for the case of representing how this formulation works, assume that I have Z, you have X, you use G theta of X and reach Z value. You have Z, and you start passing this V through each of your transformation. I pass it through F1, and I know that Z is Z, with this VR notation, Z is Z0, and I pass it through F1, I have Z1. And I can calculate here, when I have the input and the output of this F, I can calculate its Jacobian. Right? I can calculate the Jacobian. The Jacobian is this d pi d matrix. The derivative of output with respect to the input, which is a matrix. Okay. The next Z1 is passed through F2. Then I can calculate Jacobian of F2 for the arbitrary layer L. ZL minus 1 passed through FL. I have ZL and also the Jacobian JFL, and finally the last ZL minus 1 pass through FL and generate ZL, which is X, and you have the Jacobian GFL. What is the Jacobian of the complete transformation? It is the multiplication of these matrices and pay attention again to the order. The last is F1, the Jacobian corresponding to F1, and this is the resulting Jacobian matrix of the composite transformation. And we know that it is inverted. Okay, on the other hand, if I have the if I have the forward transformation, I have an equivalent reverse transformation, okay? And denoted by G theta. G theta is composite of G1. We know that the order is changed. G1 is the inverse of F1, but the order is reversed. So F1 was in the forward transformation was here, G1 is here. And until GL, okay? Again, I need the Jacobian of this matrix to use the other formulation for calculating the data likelihood. So I need to calculate the Jacobian of this transformation, this composite transformation. Again, chain rule can help. Chain rule can help, starting from this one here. You input X into the Jacobian calculator of the last transformation, which is JGL, Jacobian of GL in the input X, then the Jacobian of GL minus 1 in its own input, which is ZL minus 1, until the last one, this is G1, the Jacobian of G1 in the input Z1. So again, I can calculate the Jacobian of the resulting transformation, the resulting inverse transformation, okay? And then when I have this Jacobian, I can calculate the probability of each data point using this formulation. Everything is clear, yes? Any question? Okay. Again, we start with X here because we are in the inverse. In the inverse, we start with X, which is ZL. ZL pass through GL and generate ZL minus 1. I know that this transformation, this invertible transformation, has its own Jacobian matrix, which we call J of GL. Here, one D is missing. It is of the dimension D times D. And I know that I can progressively calculate each of these transformation and these Jacobians. And then the resulting Jacobian of the composite transformation is the multiplication of the Jacobian of each of the blocks. Everything clear? Just pay attention to the order. The order is very important. Okay. This is how we use normalizing flow. So just we need two things. First, learning. Second, the design of each of the transformations. What is G1? What is F1, F2? What are the options? What are the options proposed? You can think of any invertible transformation here. But you can see that there are several interesting that provide with some interesting Jacobian calculations. Any question? Okay. So let's recap normalizing flow. Why we call them flow? Why? Because the data flew through several invertible transformations. Because of this flow, we call them normalizing flow. Why we use normalizing? Because these normalization coefficient. Because if you flew through the transformation, the area will change, as we see before. Okay, and you need some modifications for the so that the area is preserved in the target space. If you have Z and then go to X and have our first intuition without normalization, we see that the area under care for the PDF here, the integral of p theta f, this was not the correct approach, but we see that it is not equal to 1. So we need some normalization. The normalization justifies the name for normalizing flow. They are normalizing flow because the data is flow through transformation, and each of them normalizes the PDF. Okay. Let's think of the tasks, how we can apply our task our deep generative modeling task to a normalizing flow model, generation is very simple. Why? Because Z is coming from a easy to sample distribution. For example, normal, a standard normal, but we know that Z is of the same dimension to what you observe. You can easily sample this Gaussian distribution and have this Z, and then you pass it through F theta, and then you have samples from your data distribution. Assume we have a trained model. We will see how we can train it. Assuming you have a trained model, it's just needed to sample to generate sample from the base distribution, pass it through the transformation. Everything works. You have data from data distribution and your model distribution, which is near to the data distribution. Okay, so this is the sampling part. How is the density estimation part? We will see it several times. First, X, for example, you have X, you pass it through G theta, and we call it Z. We know that G theta is the inverse transformation, so we can transfer from X space to Z space. And then we calculate the PZ in that point. What is the problem with PZ of G theta X? The problem is that it is not normalized yet. It needs normalization factor. It is again our mistake in the start of this course that here is 1/4, here is also 1/4. Do you remember? This is our problem. So this is not a distribution yet. It needs to be normalized. So what happened? I calculate the Jacobian of this transformation, call it Jacobian of G at the point X. Then take the determinant, take the absolute value. I have this number, and if I multiply them together, you have a valid PDF value. Okay. So how we can have PDF value at the point X or density estimate with this procedure? First, you pass it through the inverse transformation G, then calculate the PZ at that point, then generate the normalization. Multiply them together, it is your valid PDF value in that point. So we can calculate the density. This is the second task. And the third task is the latent vector, where again we have the latent Z, but pay attention that Z, you cannot do something like attribute vectors in Z. It is not as simple as VAE. You cannot design the attribute vectors here. For example, you have a smiling man, neutral man. You cannot design the direction of the smile in such a large dimensional space like Z, because nothing is encoded there. Okay, you just have a transformation that comes from the data distribution to a simple distribution, for example, Gaussian or uniform or anything. Okay. So we have the latent, but the latent is not as maybe usable as VAE. Okay. So what are the limitations of this for normalizing flow? The first and the most important one is that normalizing flow is dedicated and is customized for continuous random variable. Why? Can anyone talk about why this happened? Pay attention to this figure. You know, that area change is just applied when you have continuous word. If you have a discrete word, what happened? You just apply transformation. Here, for example, is 1, 2, 3. Here is, for example, 2, 4, 6. Nothing changed. No area here, because data is discrete. The transformation and the area change is responsible for the validity of that approach. Okay, so it is very important to know that this cannot be applied to a discrete word. In the discrete one, when you apply it, the area is preserved. It means that just this approach that does not work in the continuous world, it can easily be applied into in the discrete world. Because there is no area, everything is discrete. Okay? So this is the first limitation. The second one, the base distribution. The base distribution must have these two properties. First, easy to sample. Second, easy to calculate the likelihood. So we generally use Gaussian. Why? Because to calculate the density, to calculate the likelihood in the target space, you need the likelihood in the base space. So both the sampling and the likelihood calculation in the base, not in the origin, not in the observed, in the base space. For example, the Gaussian should be which is easy to calculate both the likelihood and sample from a Gaussian distribution. So you are limited to some distribution in the base space. And the last one, and another important property and limitation is the equal dimension. Because of the invertibility, you cannot go into a lower dimensional space from the original space. Why? Because the resulting transformation will not be invertible. So you need to have the same dimension for what you observed and what is your latent. So the Jacobian are very large matrices. They are D by D. The determinant calculation is of the order of 3 times to the power of D to the power of 3. The transformation should be designed carefully because any inefficiency lead to interactability of the calculations of the likelihood, and when you can't calculate the likelihood, you cannot train the model. Okay, these are the limitations for what we talk about. But assume that we have a model, how we can learn it. Again, do not pay attention to the complexity of calculation. We want just to have the approach, and then we see that what are the good options for the transformations. Okay, to learn a model, we need to maximize the model likelihood assigned to samples coming from the true data distribution. This was the equivalent to minimizing the KL between P data and P theta. Okay, so again, I can estimate this expectation using Monte Carlo estimation. So I just need to have the log likelihood of data, and then I can the log likelihood as a function of parameters, and then I can take the gradient, maximize this value, and train the model. Everything is clear how we train them. We calculate the data likelihood as a function of the transformation parameters, and then update the parameters such that the likelihood is maximized. Make sense? Okay. So let's think of how we can calculate the data likelihood, assuming that we have L different transformation composite together. You have a normalizing flow. So I want to calculate the data likelihood, and we know that the data likelihood is equivalent to the value of your base distribution in the corresponding Z. This is the corresponding Z, G theta of xi, call it Zi. This is the corresponding Z. We know that this is not normalized. It should be multiplied by the determinant of the Jacobian in that point. So this is a valid PDF value in the point xi, and you want the logarithm of this value because you want to maximize the log likelihood. And the logarithm is very helpful here. Why? We will see. Starting from the chain rule, we know that the determinant, the Jacobian of the G is the multiplication of Jacobian matrices. But pay attention that the order is not clear here, but we know the order. Okay? The order is not here, but we know the order because this prod operator does not show the order, but we know what is the order. Using the chain rule, I have this, and again, using the determinant property, we know that the determinant of the multiplication is the determinant of multiplication of matrices is the multiplication of the determinant of each of them. You can change the order of multiplication and determinant. So I have this simpler case. How can this change help me? Now I have logarithm of some multiplications. Just the ABS, the absolute value is not suitable here, and you can easily know, we can easily show that the absolute value of something, the product of something is the product of absolute value of them. So you can change the order of, again, product and the absolute value. Now you have multiplication of several terms, and logarithm here is very helpful because it can separate them. So we have the logarithm of the g theta of xi, and the multiplication becomes the summation. The summation of the logarithm of the absolute value of the determinant of the Jacobian of each transformation. Okay? So something is, it is becoming to some extent more simpler because you do not have the multiplication of matrices anymore. You see, you do not need the multiplication of matrices anymore. You just need the determinant of each of them. But it is important to design them such that their determinant can be calculated easily, because the determinant is really needed. But the multiplication is not needed anymore. Why? Because you do not need the likelihood, you need the log likelihood. Okay, so we simplify the log likelihood as this formulation, and these two terms are function of parameters here and here. The Jacobian is a function of parameters, the G is a function of parameters, so you have a term that shows the likelihood of your data as a function of the transformation parameters. So you can maximize it, you can take the gradient and maximize it. Okay? So, this is the resulting, I think, it's argmax here, this problem here, because we want to maximize the likelihood. Okay? We want to maximize the likelihood. And this is the complete problem. You know, here we have the likelihood for just one sample. Here the average over all dataset samples. This is the average over all dataset samples. You know, this summation is for the all. There are several problems here. Let's see. Yeah, you have a summation here over x over I. You have a summation here over I. So the summation is here over all the complete two terms. The summation of the two terms. I will update this slide, but pay attention that this summation is for both of these two terms. You have show the parentheses here and here, and we know that. What is the ZIL? ZIL is everything is talking about xi because it has subscript I. And L show that in which layer you are. L is the layer in the transformation orbit. Okay? Everything is clear? Makes sense? Okay. To update from the, this is based on the reverse transformation G. If you want to work with the forward transformation F, you will know that just this absolute value has a minus is inverse. The inverse of this absolute value, we need that. So in the logarithm is the negative. So everything works by changing the plus here into the minus, and this is again the forward transformation. Pay attention again that this summation is over both terms. This summation. And yeah, I made a mistake here. This is over both terms. So we see that how we can calculate the objective of the training as a function of parameters, and then you can take the gradient. But the most important point is what is the gradient of these Jacobian matrices. They are very important in our procedure. So now we want to enter the transformations. We know why the invertible transformation is important. We know how to calculate the likelihood. We know how to train them if we can calculate the gradient of this term. Now we want to define some transformation and calculate the complete likelihood, data likelihood as a function of the model parameters. The first one is nonlinear independent component estimation, or NIS, abbreviatedly NIS. So what is NIS? NIS is composed of two types of layers. The most important components, we have L layers. One of them is the additive coupling layer. What is the transformation in additive coupling layer? Additive coupling layer is one of, for example, is one of those FIs, FLs, F1, F2, FL. One of them is, for example, additive coupling layer. The transformation is in this way. You have the transformation f theta, which transform you from the z space into the x space. Assume x and z of the same dimension. The forward transformation is defined as, first, you select a random integer such that that random integer lies between 1 and d. And note that it can be 1, but it cannot be d. What happened? You have an input vector z. For example, in R10. Okay? You have a corresponding, this is z. You have a corresponding x, again in R10. First, you select a random integer between greater or equal to 1 and less than d. Here, less than 10. For example, you select 3. What happened? The first d element of x is exactly the first d element of z. They are copied. No change, no scaling, nothing. Okay, just copy them. Then the other elements are generated in this way. The next, so we have a figure here, but just to have them together, you copy them. Then the next part, how is it generated? The first part, here. You first copy the first d element here. Then what happened? Then apply any transformation, any arbitrary transformation, anything you want, to the first part again, and add it to the second part. What happened? This transformation changes your dimension from d, because the input is d, into d big uppercase d minus d, because it can be summed with the remaining elements. Make sense? And this m theta is anything you can consider, any type of transformation. So the first part is copied. The second part is the transformation of the first part plus the second part into the second part of your x space. So how can this form be invertible? How? Because m is any nonlinear and there is no restriction on m. Anything you think, it just obey their dimensions. Input is d, output is uppercase d minus lowercase d. So assume I have x. What is the inverse transformation? The first part is exactly the same because it is copied. So I again copy them into z, and I know m. So I know that the first part is exactly the first part in the original space. So I can again pass the first part of x from m and then minus it from the second part. This reverses this operation. You know, here you exactly have the same thing as here because they are the output of the nonlinear transformation m over the same thing. The input is equal, the transformation is equal, so the things you have here and here is the same. Here you add it, here you subtract it, and then you generate a z for the remaining part. Does it make sense how it works? Again. Here, I have the first part copied, okay? The second part, I pass the first part through any nonlinear, any type of transformation, and I know that this transformation is from R to from RD into RD minus D, okay? So here is a transformation. Then the next part is sum with this new vector. So I have a new vector and put it here. I know that the dimension is working, right? Because the dimension is D minus 1, D. Here is also D minus D. Does the forward works? Okay. Now I want to come back. How? The first part is not changed, so I can easily copy again. And I know that these three vectors are equal. I add something to Z here. If I subtract the same things, I reach to the original Z. So I should build something which is here. Clear? I should build something which is here, or something which is here. How? Same input to the same function, because this input is not different from this input. Same input to the same function generates same things. I subtract it. Here I add it, here I subtract it, again I have Z. Okay? Clear? Yes.
In the middle vector, why do they become x's in the top when they still be z's?
What?
Like x1 through xd, when it still be z1 through zd?
Yeah, it's just a notation because we want to emphasize that we are in the X space. They are exactly the same. Yeah. Any question? Yes.
So in the Jacobian, there's going to be some zeros.
Yeah. The Jacobian is very interesting here. For this transformation, the Jacobian is very interesting. You see that. And the invertibility is also, and you have some flexibility here in M. It can be anything. Any function can be used here. Okay, so this is my f function, f theta function, this is my g theta function. And let's check the Jacobian. What happened in the Jacobian? The Jacobian is equal to 1. And you can ignore it in the optimization. How? We know that the Jacobian, if we have these these figures and this text together, it was really great. But remember this for this form. Now think of the Jacobian. The Jacobian, it has 4 blocks. Why? Because we want to talk about these separately, because they have their own transformation, okay? We know that the first part is the copy. So this block is exactly 0. This is copy. This block can be anything because it is related to your M. It is not important. But the most important is the new part, okay? We know that here how XD is generated. You should know that what is XD, how ZD affect XD. And you see that here, ZD is multiplied by 1 and appear in XD. Is it clear?
No. The input of M function is independent of ZD plus 1 to Z.
Yes, sure, yes. You have no dependency. The things that you said lead to the fact that this part is also upper triangular, okay? But why the main diagonal is equal to 1? You should, let's talk about, we are here. and assume that I am in the main diagonal of this box. This is what is this value here? This value is the derivative of x d plus 1 with respect to z d plus 1. Here, what is this value? Is it clear? It is 1? Yes or no? It's just an addition. A vector is added to z, the second part of z, and generate x, the second part of x. So each element with its corresponding index is just an addition without any multiplication. So this value is 1. And also pay attention to the part that we talk about. Why this is why this is an I? Because each element, how they relate to each other is just through a summation. You know, there is a one-to-one summation between these two vectors. So the Jacobian of the last part, this block is I. This is I, this is anything not important, and the most important point is that the complete matrix is lower triangular. And a lower triangular determinant is the multiplication of the element on the main diagonal. If you not see it before, then the determinant of the matrix that has a 0 element on the upper triangular is equal to the multiplication of elements on the main diagonal. Maybe I should remember it in the foundation part. And this determinant is equal to 1. And everything is very simplified. Why? Because it is not even a function of your theta. And if you just use this type of layer, even lots of them together, you do not need to think about the Jacobian, the determinant. You just need the maximization of P g theta of x, which is the first. But it is really expressive. You know, this transformation, although it has a Jacobian equal to 1, it is expressive, and you will see that they can model, for example, digits, images of natural scenes, and something like that. Clear? Okay. But in the paper that Mies suggests that there is also another type of transformation. As you see here, there is no, let's say, because of the diagonal is equal to all of them are 1, there is no volume change. You know, there is no scaling. There is no area change. In the second layer, they also introduce another layer. The layer is rescaling layer. In the rescaling layer, they just have element-wise multiplication. Very simple. You just have d of these parameters. So the transformation has d parameters, and each element zi is multiplied by the corresponding theta I and generate xi. This is the transformation, and if they are not 0, which is our constraint, they cannot be 0, the transformation is invertible. You can divide x by theta I and generate zi. So it is valid for our formulation and normalizing flow model. Okay? So if f theta is this one, we understand that g theta is the inverse, and we know that theta i's are non-zero. So this is the rescaling layer. Each element multiplied by theta, corresponding theta, and generate the output. And if you want to go from x to z, you can easily multiply xi. You can easily divide xi by theta I. So this is valid. How is the Jacobian? The Jacobian is also simple. Well, how? Because this matrix is diagonal. Every element is just related to the corresponding element with the same index. So it is diagonal, and non-diagonal of the diagonal elements are all 0. And we know that for the diagonal matrix, the determinant is the multiplication of the diagonal elements. And also pay attention that we work with the logarithm of this term. So the multiplication will also be transformed into a summation. And everything will be very simple. So although the parameters of the transformation appear in your objective function, but their dependency or the functionality is not very complicated. You have the logarithm of each of these terms because the summation, the product transforms into a summation because of the logarithm. You have the log of theta I, and the log is very easily, you can easily calculate the gradient and backpropagate it. Okay. So let's see how NIS can be applied in the real-world application. Just pay attention that we previously have very limited performance. Now you are in the world of faces, so they have some improved results. In the case of autoregressive models, you do not see these types of images. So it can be a improvements over the previously autoregressive models, although we know that autoregressives are well suited for sequence data. Yes?
So what was the definition of the NIS here? So
the NIS is a composition of several additive and scaling layers. Yeah, the architectures maybe have 6 or 7 layers, for example, resulting into this one or this one. Yeah. Just the basic block is just there. They can be used interchangeably or the different types of architectures, and the result is, we know that the result is exactly invertible, because each of them is invertible. Oh, here the architecture is also written. The architecture comprises 4 additive coupling layers and 1 rescaling layer for them.
Each layer in any type of NIS structure should be additive coupling for the rescaling.
Yeah, there's definitely, yeah, but we have lots of invertible transformation that can also, they can easily calculate with Jacobian, and they are suited for the flow models. Yeah, it is not the only option. Okay, and you can see that we have MNIST here. These are generated samples, you know. Pay attention that these are not from the data set. These are all generated, yes.
What is M theta that we use?
M theta? I do not know the exact form of the M theta, but it can be anything. And it means that you have any types of deep neural networks can be used as M theta. It means that M theta itself can be a complete deep neural network. Yeah, but you can check the paper. What is the exact architecture for M theta?
But it's pretty complicated.
Yeah. It's complicated and it is not needed. It does not have any restriction. Yeah. So this is the result of sampling from MNIST. This is the result of sampling from TFD dataset. And you can check this paper for more results. Yes?
Should M theta return single delta?
No. M theta is from RD. It is both the input and output are vectors. RD to RD minus D.
Okay.
Yeah. The input and output are both vectors. It depends. If you select, because D can be only 1, we see that D is between 1 and less than D. So it can be 1, so the input may be a scalar. Okay. This is the result of sampling. These are also samples. I know that this is not very maybe fascinating, but pay attention that these are only the initial results of these types of model, the first paper. So there are lots of people, and also they are continuous flow models that we do not have time to pay attention to talk about in this class, but they work very well, even better than the fusion models in some aspects. So If you are interested, I think there are several professors here that work on the topic, and there are several great PhD students here that work on the flow models, and I can introduce them to you. Okay. Let's talk about an application using NIS. Just the last one. Yeah, the last one. Assume with the simple case of the NIS model, I want to inpaint an image. What is image inpainting? Image inpainting is a task where a part of your image is missed, or it is noisy, and the signal to noise ratio is very low. It means that there is no content of image in those parts. Assume that you have a trained model. Now we know that how to train a model over MNIST using NIS. And assume that you give a sample X, where XO or X observed is the clean part, and XH or hidden is the corrupted part. Find the estimate to the corrupted part. This is your task. You have an image. Let's see some images here. These are exactly from this reference. You can check it. Assume that I have an image like this. The first part is missed, the first upper part, or anything. For example, here you have part all over the model. And previously, if you remember, we can fill these pixels using, for example, autoregressive models. Do you remember? We start from the autoregressive model until the first corrupted pixel, and then sample from it, and then fill it. Now we want to. Now here you can fill any types of corruption. How? Pay attention to the formulation. I have a p theta of x. It is trained. It means that theta is fixed. You do not need to train theta anymore. You have theta star. The best theta is given to you. Now you want to find a maximum a posteriori estimation. Maybe the name is not very familiar. What do we mean? We mean that we want to maximize this your model over the hidden space, hidden part. What does this distribution show? This distribution talks about what is the probability of the corrupted part if you have access to the clean part. In other words, here, what is the probability, for example, for this image, what is the probability of this part if someone tells you that the half of the image is this? You have something in mind. It is a circle, maybe it is a 0. Which one here? But maybe it is a 0. So you have some intuition about the missing part, and the model also have some intuition. But how to use that intuition and that ability of the model? This is how you can use it. I want to maximize the model posterior over what I missed, hidden part, condition on what I observed. I know that using the Bayes rule, this distribution is equivalent to maximizing the joint over the probability of observed part. And what is the joint? The joint is exactly what you have. This is the joint, because the observed and the corrupted part together are your input. So the joint is your input. In other words, the maximum a posteriori approximation to the hidden part is something that maximizes the joint. It means that you have a model, the model gives probability to any filling. You can fill the missing part with anything. But each of them give you a p theta of joint. And the one that gives you the maximum means that that's the most probable option.